applications of remote sensing for crop yield, crop stress, and as well as pest and disease application. Our condition, my field of expertise is a little bit different from the previous studies. We work on a large scale, like large regional scale. Pardon, am I audible to everyone, Mr. Stanley?
Yes, yes, sir.
Yes,
Yes,
sir.
sir.
I
Audible.
hope I hope
Yes,
I'm
sir.
Yes,
You're
audible.
sir.
audible.
Yes,
Okay.
sir.
Um, Earlier, it was the studies were more on a field scale, like individual plot or individual plant scale. But in our case, it is different. We study majorly with respect to large area scale. In those aspects, I have prepared a presentation. I will share that presentation, and I'll be briefing about brief information application of this machine learning and satellite wavebands in brief. I'll be giving a brief introduction, and after that I'll be explaining you people about the case studies we have worked with in during my PhD as well as post my PhD. It will be fine for you all of fine for all of you, I guess. Okay, I'll be sharing my presentation now. Okay, I think my presentation is visible for everyone.
Yes, sir. Yes, sir.
Yes,
Visible,
sir.
sir.
Visible.
Okay, in my presentation, I will be starting with the brief information on machine learning in agriculture, and next thing, the satellite wavebands and their application in smart agriculture. And I'll be giving you 2 or 3 scenarios of application of both machine learning as well as satellite wavebands for yield estimation as well as the crop insurance in Karnataka. And I'll be wrapping up the session with the research gaps. What are the major research gaps with respect to application of these machine learning as well as satellite wavebands in smart agriculture. First, coming to the smart agriculture, what is smart agriculture? It is data-driven farming, satellite information, weather information, as well as machine learning based information. Application of these three are together for predictive decision making. Earlier, as you all aware, that agriculture is majorly dependent on the expertise of the farmer with respect to that particular crop or the traditional agriculture, what we can say, is dependent on the expertise of the farmer. The farmer used to make the decisions on different agriculture practices based on only expertise. Last year, during this nakshatra, this Tithi, I used to sow pigeon pea. This year also, I'll sow this. We have received 2 rains, so I'll sow the pigeon pea. But he will not be aware of the forecasts or the variability within the soil within the field. Under such conditions, the farmer used to get the variable yields. One time, he might get during high rainfall years, he might get good yields, but most of the cases, he might get lesser yields. Because of these unprecedented challenges, as I have given in the slide, that is majorly climate variability and another improper decision making. Uh, the need for this smart agriculture comes again in the figure, like because of in recent days there is much climate variability as all we are observing, and there is a increase in population, and there is a shrinkage in resources, like groundwater and arable land, as well as along with the climate variability, the fluctuations in the rainfall. Though we are receiving the normal rainfall, the total quantum of the rainfall in a year, but its distribution also getting deferred year to year. Under such conditions, the crop might face a stress during one of its growth stages, leading to the yield losses. Along with this, there is a labor shortages because of several reasons like migration to cities. Though we have increase in population, but we are also facing the labor shortages because of migration to cities, reducing farm workforce and production pressure. Because of all these 3 reasons, like climate variability, resource scarcity, and labor shortages, the production pressure is increasing, and there is calling for a urgent need to produce more product with less resources. And this inspires us to make the use the resources with more so that we can produce more outputs. Uh, but here the smart agriculture comes into picture. To define smart agriculture, uh, it is smart agriculture. It is the utilization of data science and scientific models to support from farm decisions. It doesn't replace farmers. It supports the farmers. Just it supports the decision making process of a farmers. Instead of asking what we did last year, just it supports smart agriculture. Ask what does the data say. So what production practice we can take this year so that we can produce maximum. This is about smart agriculture. Here we are taking the advantage of data and data sets from different models or different sources for predictive decision making on particular crop management practice. Then coming to the machine learning, the core definition, all might be aware of machine learning. The core definition of machine learning is simply means it is teaching computers to learn patterns from data sets we give in and use those patterns to predict the or classify new observations. Like unlike traditional like a quadratic or simple linear regression, machine learning does not require us to define relationships explicitly. Uh, it is not a magic. It's simply statistics at a scale powered by high speed consumption. And for learning, teaching the computers to learn from patterns, there are different data sources nowadays. First data source is satellite indices. Second is weather data sets, soil property information, crop information, crop phenological stages. You might be aware of different crops. They're classified into Rabi and Kharif because based on the water requirement and growing light requirement, photo period requirements. You might be aware of all these things. So crop traits also different for each crop, and we can use the growing indices, growth indices like phenological indices, water use efficiency, growing degree days, and those as a numbers for putting in the data to so that to teach the computer to learn from these data sets. And along with these satellite images, weather, soil, and crop information, we can put in the management history by for it if you train a model for but using these the information and we evaluate, we can modify the management and so that under different management scenarios what will be the output, we can generate those information also by using machine learning models. There are three different types of machine learning models. First one is supervised learning, and second one is unsupervised learning, and third one is deep learning. First, in supervised learning, just we give inputs to get a known output. Okay, we teach the computer with labeled example. For example, in agriculture, for yield estimation, disease classification, just we teach the computer. Earlier, the leaf color was yellow. We give the number. Assign certain number to yellow leaf, and we go on feeding other leaves so that it detects the how many were affected by disease, how many had a yellow pigmentation in them. It goes on detecting how many leaves were under such. These are supervised learning. Here we use green yield prediction, disease classification, estimation of leaf area index, and the nitrogen in agriculture crops. For there are different supervised learning models are there, random forest, support vector machines, gradient boosting, different models are there. Second classification is unsupervised learning. Just we make the computer to learn the patterns amongst existing between the dependent and independent factors. Okay, computer itself discovers the hidden structures in the data sets we have given into it. For example, major applications are agroclimatic zoning, crop growth clustering, and soil variability mapping. Major application in K-mean cluster analysis is the unsupervised learning. Here, there we had an example of agroclimatic zone delineation, which considers different agronomic, climatic, and other management factors in a particular region. And if we use the K-mean clustering technique, it clusters the It identifies the similarity and dissimilarity between the clusters, and it helps us to redelineate the zones. Under such conditions, unsupervised learning, and here the relationship between the independent and dependent factors will not be aware of the factors. Under such conditions, unsupervised learning is used. Another thing is deep learning, to have the idea of complex layers which mimic human visual processing. These techniques are used for agriculture applications in plant disease recognition, drone object detection, and high resolution satellite vision. And these deep learning techniques in trend in recent days are known for their handling ability to unstructured data like images better than traditional machine learning techniques. Okay. And next, coming to the workflows in machine learning. You might be aware of major workflows in machine learning. The core concept is okay. First, in machine learning, for machine learning, first we have to define a question, clarify the specific agriculture problem to solve. What we are targeting, and what are the data sets we are having, so that whether we can generate the required output or not. If we define that question, we have to start collecting the data, field based observations or satellite observation, or weather data sets from either from direct observatory or from satellite images. And next comes the clean and pre-processing of the data, removing the noise, whether we can check for the normality, we can check for the standard deviations, whether they have the deviation is normal according to us or not. We will be having some idea about the data sets, and we have to clean. If it is having more number of outliers, we have to use a specific technique for removing the outliers also. We have to using multiple different statistical methodologies, we have to clean the data set. And using the clean data set, we have to create a futures, and use the uh, keep creating the features, like using the clean data, we calculate certain indices, bands, and temporal metrics by using the clean data. And after that, creating the indices, we can deploy and monitor the machine learning the data sets to implement the model and track real world performance. And after training the model, we have to check it for after training the model, we have to test it for its vigor by using different statistical evaluation methods. And if meets out our evaluation testing requirements, then we develop the evaluate the models for different variability in different inputs, like the independent factors, how they affect the dependent factor, which is yield in our case. Okay. Next, coming to the remote sensing. Remote sensing, it is the methodology, it is the process of observing the Earth without touching it. Like satellites are using the satellite remotely spaced. The distantly placed satellites are sensors to measure the how surfaces reflect or emit electromagnetic radiation, like how the objects on the Earth uh, reflect or emit electromagnetic radiation. So major platforms like sensors in India used for different agriculture purposes are Landsat for historical data sets, longest, and it started from 1980s, and ideal for time series analysis. And ResourceSat, indigenous platform widely used for national crop inventory. And Sentinel-2 data, highest resolution with excellent red edge bands. And Modis data, coarser with a coarser resolution but high temporal frequency for monitoring. And some commercial platforms are also available: PlanetScope, Prisma, or Hyperion. These for biochemical and high frequency microsatellite constellation data informations are available through different sensors in the India. Let us discuss about the major wavebands which we study within remote sensing for agricultural insights and applications. first major band is blue band. It is around, it's near to, as you all aware about that. It's near 450 to 520 nanometer, and it majorly helps for identifying the vegetation, whether there is a vegetation or it is not a vegetation. It's a bare soil. Can it helps for studying the canopy cover, and whether it is full, and its classification, whether it is full or low or sparse. And it's majorly applied for early stage. The sensors we observing blue bands are majorly used for early stage crop mapping, bare soil versus young crops, water logging or shallow water detection in agriculture field. Uh, it is rarely used alone, but it is important for cleaning and correcting the signals from signals for utilizing in other applications. The next band is green band. It represents 520 to 600 nanometer in the electromagnetic spectrum. It uh, it is the peak measure of a peak reflectance of a vegetation in visible range. Therefore, it is directly proportional to leaf pigmentation concentration in the field crops. It gives the vegetation vigor, and it gives to response to chlorophyll, but less stronger than the red band next we are going to study. It has applications in crop vigor estimation, green NDVI estimation, visual crops monitoring. Next important band is red band. It is around nearly 630 to 690 nanometer of electromagnetic system. It is shown by the canopy, which is having strong absorbed by strongly by chlorophyll, and very sensitive to plant health. Healthy plants, that is, healthy plants absorb red light for photosynthesis, and stressed plants reflect more red light. So we employ this red band for NDVI calculation, and which is having more major application in stress detection, crop growth monitoring, yield proxy, nitrogen deficiency, early drought stress assessment, and disease onset. Next major band is red edge band. It represents 700 to 740 nanometer. The transition zone between red absorption and the near infrared. It is extremely sensitive. It is recently used in satellite image assessment. Extremely sensitive to subtle physiological change. Therefore, it is majorly studied for nitrogen deficiency studies, early season droughts, disease onsets. Therefore, it is helpful in early warning system of all these nitrogen deficiency, droughts, and disease management. The final and important is band is near infrared. It is representative of internal leaf structure, canopy density, and biomass in a cropped area. It is majorly used for healthy and strong near infrared, healthy or dense canopy, showing which are showing strong, directly proportional to strong near infrared, high near infrared reflectance. Therefore, it is having applications with respect to biomass estimation, canopy structure, NDVI, and yield modeling. Uh, as all we know that these bands are not only for visualization, just they supply inputs for machine learning. We use these factors, the indices developed by using these bands, and we put them into the indices, major indices, as I was explaining, and NDVI, like normalized difference vegetation index. It is the from measure of absorbance or reflectance of near infrared band, enhanced vegetation index, nitrogen stress sensitivity, normalized difference water index, soil adjusted vegetation index, and these all we calculate the satellite these indices as a independent factors, and yield will be our dependent factor. But after that, we will be analyzing the data sets using putting in these data sets into machine learning platforms, and we are going to detect the patterns between the index as well as yield, so that we can assess the yields in a regional scale. There are several usage cases of satellite data sets, satellite banks, and machine learning for different yield estimations in India. First one is rice. As you all know, that rice is the staple crop, having higher having higher response to the crop climatic conditions, and timely, therefore making it timely monitoring as a critical for national food security planning and export management. Yeah, using Sentinel-2, they used Sentinel-2 for accurate acreage estimation, and the growth stage for detection of transplanting, tillering, and heading sets, where they used Sentinel-2, and based on the data sets, like whether the acreage estimation, they used it for forecasting, and as well as the damage assessment, like mapping flood impact on low-lying areas. And also for nitrogen stress and regional yield estimation, they have used. Coming to the our work with respect to yield estimation, rice yield forecasting in major growing districts of Karnataka, which the paper was published in 2023, in which we had used this weather data sets, and we detected the patterns between yield and weather data. Majorly, we had taken several years, like 1980 2021 data set, annual yield data sets for 11 major rice growing districts of Karnataka. We compared SML, simple multiple linear regression, as well as ANN models, and by calibrating and validating them, and we forecasted the yield, and after that we compared the yield. As you all know that the climate factors are not having direct impact, like solely not having the impacts on the yield. So we calculated the weighted and unweighted weather indices. For unweighted weather indices, we directly placed the weather parameters of weekly weather parameters of during crop growth period. For calculation of weighted weather indices, we just correlated the yield with long-term yield with long-term weekly weather data sets. We multiplied the correlation factor with the weather weather data, so that we get the weighted weather indices. We used around 30, 15 unweighted weather indices, and 15 altogether 30 independent factors for predicting the yield, rice yield in 11. As I was explaining before, machine learning, we had to do some sort of cleaning, and we had to check for suitability of data set for our application or not. So first we did normality test and normal QP plots for quantile plots for different Kharif rice yields in different major growing districts of Karnataka. After satisfying normality only, we went for SMLR as well as neural networks. Okay, as you all know, ANNs are better than any other model. So as it utilizes the it assigns the hidden weightage to the hidden relationship between the dependent and independent factors. We used feed forward machine with a feed forward ANN with a single internal node, and there was a less difference with respect to observed and predicted yield as in ANN, as compared to SMLR, making ANN as a better model for yield forecasting with respect to rice in Karnataka. Second application is yield estimation based on technology. As you all know that crop yield, this is the methodology followed for crop yield estimation under Prime Minister Fasal Bima Yojana for crop insurance for issue of crop insurance. Earlier, the crop yield estimates were dependent on insurance unit IU. They used to group the lands into insurance units from the basis for which formed the basis for crop loss assessment and payouts under PM FBOI. In crop insurance units, they used to carry out crop cutting estimates experiments, and based on the yield or growth observations recorded in during crop cutting experiments, they used to give the insurance for the crop losses in India. But this methodology had several limitations, like the limited number of samples were drawn from these crop cutting experiments and leading to higher standard error. It was time consuming and manpower intensive. So, and also the methodology was prone to human and operational errors. Uh, Looking into these limitations, we started through KSRSAC, we started application of satellite images, satellite information for this yield estimation under this PM FUI. Government and private agencies developed technology-driven yield estimation models using remote sensing. I will be explaining those things next. Using remote sensing, GIS, and data science approaches, we conducted different. We conducted pilot studies for especially rice yield estimation during 1920, and wheat in North India was conducted, and the expert committee evaluated this yield estimation, and recommended 5 scalable approaches. And nationwide, they are having plans for rolling out this methodology for different crops in after 2023. This is the flowchart of the methodology we had used during for crop cutting for yield estimation. We used different satellite products for different the vegetation measures observations. For example, satellite reflectance used for vegetation and water indices, for calculation of NDVI as well as LSWI. FAP fraction of absorbed P for through body. We use it for fraction of absorbed photosynthetically active radiation, and yes, solar radiation for inside 3D we had used. Using these satellite products, we got a interrelationship between the crop yield as well as the growing season stress, and through that we were able to estimate the yields. Next use case is maize. Maize is like compared to paddy, maize is highly sensitive to moisture and especially and nitrogen stress. Moisture stress till knee-high stage and nitrogen stress during entire crop growth period. Therefore, making it important to measure precision monitoring during critical growth stages for higher yields and input optimization. In maize, the satellite products are majorly used for nitrogen stress estimation, leaf area index estimation, yield monitoring, and drought watch. Next is sugarcane monitoring. Here also, it is since it is a long duration crop with having higher biomass, its long growth cycle and dense canopy creates unique monitoring challenges. There should be more number of frequencies of visiting the satellite sensor to the field so that we can have more number of temporal data for having exact estimation of, since it is long duration crop, for having exact estimation of growth and stress. We should more frequently we should visit the field for higher spatial variability because of higher spatial variability and dense canopy. Key capabilities of application of these satellite wavelengths is crop discrimination, plant cane, or whether it is a new ratoon crop. As you all may be aware of the ratoons and planted cane, the ratoon crop first several years, first year the plant cane yields may be low, and second ratoon crop, first and second ratoon crop, the yields may be higher, will be higher. After that, the yields goes on deteriorating. For identifying such plant cane or ratoon crop, the satellite images, the satellite wavebands help, and thereby they support for decision making whether this year the entire the sugarcane yield from a particular region will be high or low. And for biomass estimation, as you all know, that sugarcane trash, the burning of sugarcane trash in major growing areas is causing a major environmental effect. We can estimate biomass, and we can using the biomass outputs, we can have a particular information like how we can process it, how we can um, distribute among the different agencies so that they can process it further. They can create compost from them. And next application is health assessment, monitoring diseases outbreaks, major diseases in sugarcane red rot. It is many studies have been conducted with respect to this. The sugarcane with the disease having different patterns than the healthy vegetation. And another thing is lodging. It is also showing there is a difference in large crop and the healthy crop. Using NDVI, NDWI, and thermal bands, we can use those satellite products for water stress estimation also. For water stress, thermal bands combined with NDVI provide an early warning for moisture stress critical during the grand growth, and the stress should not occur during the grand growth phase, so that there will not be any loss in sugarcane. Shortwave infrared bands correlate strongly with crop moisture and lignin content, helping to estimate harvest readiness and potential sugar recovery. Therefore, the satellite applications are higher in sugarcane monitoring as compared to comparatively higher in sugarcane sugar and rice as compared to other crops. Next is pulses. These pose a special challenge for satellite image based applications. Uh, Pulses majorly chickpea, pigeon pea, lentils are having lower canopy crops with significantly exposed soil. Their spectral signal is weaker and harder to separate from the background compared to dense cereal crops, which we studied earlier. Because of we get mixed pixels and weak spectral signature, making it a special challenge. But currently, they have made some progress with respect to applications. Crop mapping, improved mapping of cluster bean, black gram, and green gram they have carried out. Phenology using temporal NDY metrics to capture, they have captured short flowering windows, and stress detection also is under study. Uh, SWIR and red edge combinations significantly have improved the detection of moisture stress in pulses, which is critical for rainfed pulse crops. There is a research job developing pulse specific thesis, optimizing for low leaf area index rather than generic NDVI is key for future development. Then for precision, for application of machine learning and the satellite wavelengths in precision agriculture, there is a scope. Especially precision agriculture is nothing but identifying the variabilities within the field so that we can divide the field into management units, MUs, and we can concentrate on that those particular management units so that we'll be able to get uniform management entire throughout the field, and so that we can get normal yield throughout the land. Precision means here we will be considering within field variability, and through satellite images or through physical observation, since it is difficult to assess this within field variability using physical observation, we use satellite images for identifying the management units within the field using satellite images. For those may be applied, the outputs may be useful for variable rate fertilizer application. For example, part of a field is suffering from the major nutrient deficiency like the NPK. By mapping the nutrient deficiency zones using satellite indices, we can improve the application in that, increase the application in that particular piece of land. And if some part is having higher nutrient content, we can reduce the nutrient application in that particular part as well, so that we can manage the resources effectively with the maximum yields. Next thing is water management. It is also similar to NPK application, but here indices, vegetation indices in NDWI and thermal stress indices are used to improve the crop water use efficiency. And next is disease and pest early warning. As you all know, the disease outbreak is not a a matter of single minute or single day. It is the sequence of many many physiological processes. It starts with a primary symptom, secondary symptoms, and at a single time it start spreading through to the entire field. Um, before it's spreading, we can identify using spectral anomalies and hotspots before visible damage spreads across the field. So the remote sensing is having application with respect to these things. And as I was explaining earlier, the major application is crop insurance and assessment and agroclimatic zones. Crop insurance objective and rapid damage assessment for claim settlement using pre and post event satellite imagery, and agroclimatic zoning generating site specific crop advisories by combining soil health data as well as local weather patterns. Coming to the future directions for application of these ML and satellite bands is hyperspectral sensing, multi-source fusion, digital twins. Like hyperspectral sensing is nothing but moving beyond broad bands to narrow spectral signatures, detecting biochemical traits like pigments, proteins, and detailed nutrient profiles. Multi-source fusion is seamless integration of satellite, drone, and Internet of Things IoT sensors for hyperlocal real-time decision making. Digital twins is creating dynamic virtual replicas of field and crop digital passport to simulate scenarios and track life cycle history. Um, Instead of moving, this application methodology is instead of moving depending on black box model like the ANNs, the RFs will not be having a estimate of what is going within the system, how it is able to produce the outcomes. So they are called as black box models. Application of this ML like satellite images, by application of this satellite images, we will be moving from black box predictions to transport logic, essential for gaining policy maker trust and verifying insurance claims. And coming to the major limitations and practical issues with respect to application of this machine learning and satellites, though they have immense potential, their real world deployment faces significant technical and ethical hurdles, like operational hurdles, like monsoon cloud cover. In many cases, though the sensors are technologically evolved, in many cases monsoon cloud cover, because of monsoon cloud covers, the optical sensors will be blinded during key growth stages, especially during kharif season, creating some data gaps which disables us to know the relationship between the particular dependent and independent factors. Dependency and ground truthing. Accurate models require expensive, time-consuming field calibration and validation. Limited transferability. Models trained in one agroclimatic zone often fail when applied to new regions, because the agroclimatic zones will be different for with respect to the edaphic climatic management and crops and cropping systems grown in that particular area. So they will be having limited one model. The model developed in zone A will be having limited applicability in the zone B, because of these intricate relationships and resource intensity, high costs for less than 3 meter imagery, and significant computational overhead for deep learning. As you all know that Indian farming is entirely fragmented. And the fragmentation is going on still. The farmers are having smaller land holding. Under such conditions, we need sensors having higher resolutions. Higher the resolution, more will be the cost of estimation. Under such conditions, these operational hurdles come across. And next, ethical and strategic hurdles are data privacy, like costs versus benefits, and black box problems. The data privacy, who wants the farm data, protecting the small orders from predatory surveillance, and the cost versus benefit, whether the methodology we had followed is useful for ensuring digital solutions and affordable or actually profitable for marginal farmers or not. And the black box problem, I had explained that farmers and policymakers hesitate to trust the decisions made by opaque algorithms like sensors. They will not be able to trust us when we say we had developed and this was the machine learning technique we use. And they want some sort of a reason. So, as scientists, we are role is not just to code, but to build robust, transparent, and explainable systems. Coming to the future directions of these applications, I had explained this earlier, I think, that is spectral sensing, multi-source fusion, and digital twins. Coming to the conclusions, transformation, the application of machine learning and satellite wavebands in agriculture, smart agriculture has brought a transformation in analytics. Like machine learning is actively transforming agriculture analytics from reactive observation to proactive intelligence and invisible revealed satellite wavebands like radiation, near infrared, SWIR uncover plant physiological processes and stress signals invisible to the naked eye, so that the decision making is advanced then before the losses within the plant occurs. And they are having the practical impacts in application like crop major profit like rice, maize, and all are already operational and scalable. Mm. But the field validation remains critical. We must grow truth our algorithms whenever we have developed an algorithm and where we rolled it out for usage. Uh, this is about the application of machine learning and satellite wavebands in agriculture, smart agriculture. And I request, um, I guess it's understood. And if there are any questions, you are free to ask.
Dear participants, if at all you have any queries, you can ask now.
Sir, hello. I'm audible, sir.
Yeah.
Yeah, yes, sir. So for the weather prediction is applicable for the seasonal crop yield predictions, sir.
Pardon, whether?
The seasonal crop yield crop yield predictions are there now. Seasonally, we are sowing some seeds, and then based on the weather conditions, we are giving productions like that. It is implemented like
weather
that means it is
forecasts.
workable.
Uh, Weather forecasts can be utilized for yield forecast. We can develop some sort of relationship between yield and weather factors by taking advantage of historical data sets. And based on using that algorithm, we can replace the weather with forecasted weather, and we can have an estimate of yield variability within the season. Under such conditions, the weather predictions are helpful. Other major importance of weather predictions are giving advisories to the farmers during the crop growth period itself. The weather predictions can be used whether it is going to rain in the next week or not, and observing the last week's rainfall, whether we can assist the farmer to take up a irrigation or to take care of a drainage so that he can manage the soil moisture uh, according to the need of the crop.
Okay, but I'm asking about if we are using crops for a particular season, so for 3 months a crop, 6 months a crop, 8 months crop, like that we are using now. So for that purpose, we are using weather means it is is it okay? Like that I'm asking.
You are asking about the suitability of weather forecasts, like usability of weather forecasts. Currently, none of the systems are able to give accurate weather forecasts. For a short duration, the short duration forecasts are performing well as compared to medium to long duration forecasts given by different agencies like IMD, IITM Pune. IMD is the major institute giving the forecasts. For them also, they are also having certain limitations. Like short duration advisories forecasts are better. These short duration can be used for giving advisories instead of estimating using them for entire seasonal yield estimation. For short duration weather forecast, they are using both historical data sets as well as synoptic conditions. Like based on that is also based on the satellite images only. Synoptic conditions are cloud cover or water vapor content in the atmosphere in a particular period of time. They observe those cloud movements, water vapor movement, and based on that conditions, they are going to give short duration forecasts. That's why they are having more application compared to medium to long range applications.
Okay, sir. Thank you, sir. Thank you.
Sir, one question for you, sir. Like I just wanted to ask you. I'm Trilok Reddy. I'm the alumni of the US Bangalore GKVK.
Okay.
Like how does normalized difference vegetation index that helps in the crop monitoring, so through this machine learning, as you told, like how does that normalized difference vegetation index that helps in their monitoring of the crops?
It's directly related to the greenness of the plant. Whether it is more green means, yeah, you might be aware, like the more is the greenness, better is the vigor of the crop. With crop with the better vigor, having will be able to give better
Yes,
results,
yes,
better
yes.
yields.
ಹೌದು.
Ah,
ಇನ್ ಕೇಸ್ ಅದು ಇನ್ ಅದು ಯಾವ ತರ ಪ್ರೆಡಿಕ್ಟ್ ಮಾಡುತ್ತೀವಿ ಸರ್? ಕನ್ನಡ ಬರುತ್ತಲ್ವ ಸರ್?
ಬರುತ್ತೆ.
ಅದು ಯಾವ ತರ ಪ್ರೊಡಕ್ಷನ್ ಯಾವ ತರ ಮಾಡಬಹುದು ಅದೊಂದು ಸರ್.
We use the time series NDVI from satellite, different free sources. We use time series. We train a model using previous years, and using that trend model, we apply. We use the NDVI from this year. We replaced last year's
ಲೈಕ್
NDVI
ಈಗ
with this.
ರೈತರಿಗೆ ಅದು ಸ್ಯಾಟಲೈಟ್ ಡೇಟಾ ಇಂದ ಡೈರೆಕ್ಟ್ ಆಗಿ
No.
ಹೇಗೆ
This is
ಅವ್ರು
for
ತಗೋ
farmers can't use directly these products. There should be one who is having experience with respect to handling of these products, these things.
ಓಕೆ.
And you can, being a scientist, you can use the algorithm. You can develop the algorithms and use those algorithms for advising the farmers.
ಓಕೆ. So if you don't mind, can I have your contact number, sir? Yes, sir.
When you completed Trilok, when you completed what
So I'm
what
the
you studied in?
BSc Agri from Agri Marketing in the passed out 2017, sir.
Okay, agriculture marketing. Okay. Uh,
Can
can
I
you give
maybe
me your number so that I can contact you
yes,
afterwards?
97. Can I? Shall I sell?
Else, you can share to Sujata ma'am. Later, I'll get the number from her. Else, you can directly contact Sujata
Or
ma'am.
else
So that
you just here only I'll tell, sir.
okay, you contact Sujata madam. I think better. Else, you can mail me at lingrajhuggi@gmail.com. Same as my first name and last
I
name.
will share the number.
Can you type in the chat box, sir?
Okay.
Can I share your number, sir?
The number we shared on WhatsApp?
Yeah. You can share, ma'am.
Okay, sir. Okay, I'll share.
Okay, please share on
Thank you.
WhatsApp.
Okay, sir. Thank you. I'll share.
Okay. If there are no more questions, just wind up my session. Okay.
Linga, sir, can I get your number, sir?
Sujata madam will share.
I will share in WhatsApp soon after this session.
I don't know who's the.
If no more queries, we can wind up. Professor can leave the session. So we thank Dr. Lingaraj sir for your timely support in taking this session. We thank you, sir. And so with permission of participants, I think we can continue with the demonstration of some use of satellite wavebands. I will continue with the session, and Professor can leave the session.
Okay, thank you all. Thank you, ma'am,
Thank
for
you
the
very much,
opportunity.
sir. Thank you very much.
Thank you. Thank you
Right.
so much,
Thank you,
sir,
sir.
for
Thank you very much,
insightful
sir.
sessions.
Okay, sir.
Thank you, sir.
Thank you all.
Thank you. Thank you.
Thank you, sir.
Stanley, can you please share my PPT?
Sure, ma'am. I will do that now.
So am I audible now?
Yes, ma'am, audible.
Yes, ma'am.
Ma'am, audible.
So I'll continue with the session. I'll be discussing about the use of the satellite wavebands, that is a Sentinel-2 satellite wavebands.
Is anyone sharing the PPT, madam?
Please share the PPT. Yes, thank you, thank you.
Are we still in the
So I'll be
session, ma'am?
discussing about Sentinel-2 satellite wavebands. So this can be mainly used in order to assess the soil fertility. We have mainly used in order to assess the soil fertility. You can also use it in case of to identify or detect the climate change, or maybe in case of the earth or land changes. Go to next slide. So why we require Sentinel-2? So there are many satellites such as Landsat and SAR and other satellites. So main purpose of using Sentinel-2 is it gives a high resolution optical imaging for the land or maybe for the coastal monitoring. And this is the mainly developed by European Union Copernicus program, and it's a mission of the Copernicus program. And the Landsat, it takes around 10 days in order to revisit to a particular location, whereas Sentinel-2, it revisits to a location within 5 days. So we can obtain more data using Sentinel-2, and with the high resolution, we can get the data. Go to next. So there are different wavebands which Sentinel-2 uses. There are around 13 wavebands starting from B0 up to B12. So you can see if you look at my slide. So which waveband represents what? So mainly the Sentinel-2, it focuses on the red wavebands. So because we'll be using mainly in order to assess the land changes. So land changes means we mainly focus on the red wavebands. And we also focus on B3 in order to assess the crop yield or maybe the crop changes. And to assess soil moisture, you can even make use of the short wave infrared wavebands, that is SWIR1, or you can use SWIR2. And this Sentinel-2, one more advantage of using Sentinel-2 is it spans around 190 nanometer, or in case of if we consider Landsat, it spans around only 150 nanometer. So we can get more data when we have a large area or swath bandwidth. Go to next. Go to next slide. Am I audible?
Yes, you are audible, madam.
Yes, ma'am.
Okay.
Audible.
So Sentinel-2, if we try to download the data of Sentinel-2, there are two types of Sentinel-2, that is a level 1C and one more is a level 2A. So level 1C, it is there is no atmospheric correction in case of level 1C, whereas 2A uses atmospheric correction. So we can get more clear data using if we use Sentinel-2E data set. Go to next slide. So how to get the Sentinel-2 data? So one method is either you can make use of the browser-based method. That is, you can make use of your Google search, and in the Google search, you can just give a search option Copernicus browser. So when you give Copernicus a browser, you will get a first link over there. So Copernicus. In the next slide, if you see, I have put a link over there, browser.dataspace.copernicus.eu. So this link, if you use, you will be moved to the Copernicus browser. So where you can visualize the map of entire global. So which area you want to focus. So you can try to you can either search based on the Google map or based on the map given, or you can even type the place which you want to search. So there is a when you use that link. So on the top of on the top right corner, you will get a text box like thing. So where you can type the place which you are interested in. And you can do the configuration. So I'm not able to show the demo actually because of internet issue. So I thought of giving the demo. And so you can do the configuration, and I will share the PPT with the snapshot of all the steps. So later, once we complete with the session. So we can do the configuration like whether you want to select go for the Sentinel 1C or the 2A. So on towards the left of the screen, you can find the options to set, and also we can do the cloud setting. So you can adjust the cloud. If you have a cloud setting near to 100, you can get more data sets. Sorry, more data. So if you decrease the cloud, you will be getting a less number of data. And so once you download the data or the images, so we need ArcGIS software or any other software to analyze the data set. So here using this Copernicus EU, we'll be downloading or using the images, and we need a separate software in order to perform the analysis. So the images means, of course, we'll be knowing that it consumes a lot of space, and analysis using a separate software, that will be tedious job, and also data processing. It requires more understanding on how to process the data, and how to make use of, or how to label the data, or how to get use the bands, the satellite bands. So to avoid this, there is one more option, that is you can go to next slide. Go to Google Earth Engine. Go to next slide. Putting the images, and using a separate software for the analysis purpose. We can use the Google Earth Engine. So where you will be getting the pre-processed data set. So there is no the researcher or the user need not process the data. So already pre-processed data which you can readily use, make use of it. So in order to make Google Earth Engine, we can either make use of JavaScript, or okay, so I so where that functions in order to locate the area. So I have used the map function in order to get the Google Earth Engine map. And later I'll be using a set center function where I'll be using the longitude and latitude. So 74 is the longitude of my research area, and 12 is the latitude. And I have used so in order to get the exact area, that is how much area you want to cover. So you can make use of geometry function. And this Sentinel-2, it was a mission developed by the European scientists in the year of 2015. So we'll be able to download the data starting from 2015 onwards. But initially, the data was, that is the revisit of satellite was for every 2 days. Later on, from 2017 onwards, the revisit was for every 5 days. So from 15 onwards, 17 onwards, we are able to get the data starting from for every 5 days. So here, can you go to next? Can you please go to next slide? Okay, so here I will be using the initial previous slide. So you can see that I have set I date as 2015 1 means the data is available from 1st January 2015 onwards, and final date I have set it as 29/10/2021, because this is based on my research work. So I have done this research work in the year of 2021. So I have collected the data up to 2021, that is October 29th, 2021. In order to assess the soil fertility, I collected the Sentinel-2 wave bands. So here, so once we set the dates, so then I'll be using the function image collection. So we'll be using Copernicus Sentinel-2. So we can make use of the argument here to image collection function as Copernicus slash S2, and filter the date from the initial state up to the end date. And so in order to assess the soil fertility, I have used different wave bands. So if you want to use particular wave bands, you can make use of select function, and you can give the option which wave bands you want to make use of. So I have commented this line here. So yeah, because I will be using all the wave bands, and I try to get all the wave bands, and based on the certain wave bands, I try to determine different soil parameters such as pH, organic carbon, and nitrogen. So I'll be using get region in order to function, in order to locate the area of my the function and information of a particular region of interest. So I'll be all the information of that particular which I mentioned using the longitude and latitude. So I'll be getting all the wavebands even up to gateway, including the cloud mask such as QA 10, QA 20, and QA 60. So these three are cloud masks, that is QA 10, 20, and 60. Good news. This is what I said. So getting different wavebands starting from B1 to B12, including the cloud mask QE and 2 and 60. So initially I said you can adjust the cloud mask if you are using downloading the images using Copernicus. So here there is no adjustment. We are purely writing the JavaScript code here. So which cloud mask you want to use, you can identify. So if you want to have a more cloud, you can go for QA60. If you want to have less cloud mask, you can go for QA10. Of interest and which bands we want to use. So later we need to collect the data. So here data is nothing but the wavebands of Sentinel. So whatever data we collect, in order to analyze the data or to do something the wavebands, we need to store it somewhere. So we'll be using a data frame and we'll be storing all the wavebands within the data frame. Here and I'm using pandas to data. Storing data. So to store data along with the time of access of the wavebands. So I'll be storing even the date and time along with the waveband information. And also I'll be storing longitude and latitude of interest. So we'll be selecting a certain area. So maybe latitude or longitude. So there might be some minor difference. So we'll be using some center point for the region of interest, and so near to that center point, some other latitude and longitude within the data frame, we can save as a file. So I have used a function to save it as a CSV file, and so I'll be saving within my Excel drive here. So I have used underscore CSV function in order to save all these information on that CSV file. For CSV file, then you can so you get go to next slide. So if you look at this, I have used the head function just to visualize what are the contents which will so we will see the bandwidth along with the latitude, longitude, and the date time. So which bandwidth? So you can see certain values here. So after time information, that is 52604. So you can see a value 1312, which is nothing but B1, and B2 is 968, and B3 here 837, and B4 that is 545. So similarly, we have many values for different based on different time. So once you collect the wavebands, next step is so in order to identify or to determine the pH value. So I have used certain formula. So I used different research articles which was written by other researchers. So and so I found that most of the researchers either determine either pH or maybe organic carbon. So there was no article which determined pH, organic carbon, and nitrogen. So and also we slightly modified the formula, and also we verified the value of so so this was and so you can refer my paper. I will share the name of the paper, title of the paper. So it's referred, and also the formulas I will share with you. So which can be used referred, and you can uh, uh, try to make use of different waveforms or to determine the environment. You can even use the wavebands to identify the changes in and variations or maybe the sound noise. So you can using research by using certain formulas which is written by other researchers, or you can try to write your own formula. Is there any? Am I audible?
Yeah, your voice was little, breaking. So now you're proper.
Sorry. Any queries?
Stanley, can you
Yes, sir. Yes, sir.
yeah, can you take it forward for closure of today's session?
Yes, sir.
Yes, because madam is not audible because maybe network issues.
Yes. Yes, sir. So I want to thank all the participants for your participation. There were two sessions held today, and the second session was on machine learning and use of satellite wavebands in smart agriculture. Also, ma'am has already shared the PPT in the chat. She may also share it via WhatsApp. So I want to thank all the participants. Also request all the participants to kindly note that attendance will be taken based on your Microsoft Teams join time and exit time. So automatically the CSV file will be downloaded and will be shared later by ma'am. And any other feedback also or any other PPTs available will be shared by her in the WhatsApp. So I thank all the participants for your patience, listening, and participation. We will join tomorrow.
Am I audible now?
Yes, ma'am. Audible, ma'am.
Yes, yes, ma'am.
So I'll be sharing a feedback link. So in a WhatsApp group. So I kindly request the participants to fill the feedback, and also one or two assessment questions will be there. So I request the participants to fill the form by the end of day today. Thank you, one and all.
Thank you, madam.
Ma'am, also please share the contact details of second session that Dr.
Sure, sir, sure. It will be shared in the WhatsApp.
Dr. Lingaraj Oggi sir has.
Sure, sir, sure.
Okay. The session was very excellent. So I just want, I have many raised points. So I need to check it.
Yes, I want to thank all the participants and HOD of AML, Dr. Basappa sir, and also Dr. Sujata ma'am for your patience and your support.
Thank you.
Thank you, Stanley,
sir.
for your support.
Yes,
Yes.
sir.
I thank all the participants.
Excuse me, this is Dr. Aditya. I just wanted the first two sessions PPTs also. I think Mr. Professor Trilok sir had already told that second session was good. I think even I also need the same thing. If it is being shared in the PPT in this WhatsApp or through mail, I think that would be helpful for us. That first session as well as second session. Yeah, yeah.